In chapter 3.3 previously, we were given a polynomial and we were told what one of the x-intercepts were, what one of the zeros were. We used that information and the factor theorem to find the other zeros of it. And we did that using synthetic division to find the quotient, and then we set that quotient equal to 0. So now we're going to be using that technique again, except this time later on in this section, the last couple of questions, we're going to be given a polynomial with no information. It's just going to say, here's a polynomial, find the x-intercepts. The thing is, it's not going to be able to factor nicely. It might be able to factor nicely, but it's going to be difficult to think about how to factor it. So we're going to have to use this rational zero theorem and then use the factor theorem how we did it in 3.3. Okay, so before we get to that, so just an idea of where this is heading. Before we get to that, let's just talk about this rational zero theorem. So this rational zero theorem, it's going to tell us all of the possible values that are rational x-intercepts for the polynomial. So these only deal with the rational numbers. They don't tell us anything about the irrational numbers. So the rational zero theorem says the possible rational zeros of a polynomial are going to be all of the possibilities p divided by q. So a rational number is just a ratio, it's a fraction, where p, the numerator, is the factor of the constant term, and q is the factor of the leading term. So it's going to be this little setup right here. So we have to find the constant term, so it's just going to be the number, the numerical term. Then we have to find the leading term and figure out what the factors of that term are going to be. We're going to come up with every possible combination of all of those, and those are going to be our possible rational zeros. So let's do this example. So let's list all of the possible rational zeros of f of x equals x squared minus 5x plus 6. So the possible rational zeros, they're going to be factors of the constant term divided by factors of the leading coefficient. The constant term is 6, plus 6, positive 6. So factors of 6, I'll just write that out for this one. Factors of 6 divided by the factors of the leading coefficient. The leading coefficient is right out here. It's on the x squared, which is just going to be a 1. So it's going to be all of the factors of 6 divided by all of the possibilities for the factors of 1. So now we have to think, what are the factors of 6? So factors are things that multiply to that. So factors of 6 are going to be 1 times 6, 2 times 3. So the factors of 6 are 1, 2, 3, and 6. There are also going to be negatives of that. So we can have negative 1 times negative 6 and negative 2 times negative 3. Those are also going to be factors. So the way I'm going to write it is plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Every single time we're doing these problems for possible rational zeros, everything's going to have a plus or minus in front of it. Okay, so for the plus or minus 1, factors of 1, that's just going to be plus or minus 1. Only 1 times 1 or negative 1 times negative 1 are factors of 1. So what we're actually going to do now is we're going to do every possible combination. So it's going to be plus or minus 1 over plus or minus 1. And it's going to be plus or minus 2 over plus or minus 1, plus or minus 3 over plus or minus 1, plus or minus 6 over plus or minus 1. What that ends up being is simply just everything in the numerator. So anytime you're doing these problems and it's over plus or minus 1, you essentially need to just rewrite the numerator. So all of those numbers, based on this test, they're possibly x-intercepts. They're possibly rational x-intercepts. The actual ones, the real ones, if we could factor this, that function, set it equal to 0, we would actually see that positive 2 and positive 3 are the x-intercepts, which are included in this list. Okay, let's do 2 more before we get into the other problems. So list all of the possible rational zeros for f of x, which is negative x to the fourth plus 3x squared plus 4. So it's going to be factors of the constant term, which is 4, divided by factors of the leading coefficient, which is negative 1. So this is going to be factors of 4 divided by factors of negative 1. Oops. Factors of 4, we can have 1 times 4 or 2 times 2. So that's going to be 1, 2, and 4. So plus or minus 1, plus or minus 2, and plus or minus 4. Factors of negative 1, well, that we can only get that one way, negative 1 times positive 1. So that's plus or minus 1. So once again, we have plus or minus 1 in the denominator. So we're just going to do the whole numerator. So plus or minus 1, plus or minus 2, plus or minus 4. So if this function does have rational x-intercepts, it's either going to be negative 1, negative 2, negative 4, or 1, 2, or 4. And for this last one here, we have f of x, 15x cubed, plus 14x squared, minus 3x minus 2. So possible rational zeros are going to be factors of constant term, which is negative 2, divided by factors of the leading coefficient, which is 15. So remember, the leading coefficient isn't necessarily written out front. It's whatever is on the highest degreed variable. But usually it will be out front. If it's in standard form, it will be. Okay, so this one, factors of negative 2, that's just going to be 1 times negative 2, or negative 1 times positive 2. So plus or minus 1, plus or minus 2. Factors of 15, we can have 1 times 15, 3 times 5. Also, they're negatives. So plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. So a little bit more annoying for this one. The way that we do this, because it's not just plus or minus 1 in the denominator, we have to come up with every possible combination. So for the numerator, that plus or minus 1, I'm going to give it every single one of those denominators. So plus or minus 1 over plus or minus 1 is just plus or minus 1. And then plus or minus 1 over plus or minus 3 is plus or minus 1 over 3. 1 over 5, we get plus or minus 1 over 5. 1 over 15, plus or minus 1 over 15. And now next, I'm going to go to the 2 in the numerator and give that every option in the denominator. So I'll do 2 over 1, which will be plus or minus 2. 2 over 3, plus or minus 2 over 3. 2 over 5, plus or minus 2 over 5. 2 over 15, which is plus or minus 2 over 15. So that's a lot of them, but those are all of the possible rational zeros for this function based on this test. So you're probably thinking, well, what use does that do? That doesn't tell us the actual x-intercept, it just tells us what's possible. We're going to be using that to help us find the actual ones. So the steps that we're going to be doing, first step, we're going to find the possible rational zeros, doing what we just did. Then we're going to test all of them until we find one. So we're going to do that by plugging them into f of x and see which one is an actual zero. Once we find one, we can stop. We don't have to keep on doing it to all of them. And then once we get that zero, once we figure out which one is an actual zero, we're going to do exactly what we did in section 3.3. We're going to do synthetic division using that zero that we found. The quotient will be the other factor. We're going to set the quotient equal to 0 and solve it for x. And those will be the other zeros. Okay, so let's do an example. So you can see how we're given no hints here. It just says find all the zeros. So what it's saying, what are the x-intercepts? For f of x equals x cubed plus 2x squared minus 5x minus 6. So what I'm going to do first, I'm going to set this up kind of in steps here so there's not stuff written all over the place. So I'll put find the possible rational zeros. So finding the possible rational zeros is going to be factors of -6 divided by factors of 1. So that's going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6 are the factors of 6, -6. Factors of 1, just plus or minus 1. So this is just going to give us everything in the numerator because we have the 1 in the denominator. So these are the possible rational zeros. And what we're going to do now is we're going to test all of them until we find one that is an actual zero. So I'm going to start with +1. I'm going to say is x equals 1. So I'm just using our possible zeros. I'm going to say is x equal 1 a 0? Well, I'm going to plug that in. I'm going to do f of 1. So plugging it into the function. You could also do synthetic division for it, but I feel like this might be just a little bit quicker. So 1 cubed plus 2 times 1 squared minus 5 times 1 minus 6. This actually gives us -8. So that is a big nope, that is not a 0, so we have to keep on going. So next I'm going to try 2. So is x equal 2 a 0? Well, let's test it. Let's do f of 2 by plugging it in. So it's going to be 2 cubed plus 2 times 2 squared minus 5 times 2 minus 6. So solving this actually does give us a 0. So since that one is a 0, we're actually done and we can move on to the next step. Once we know that that's a 0, like I mentioned, it's exactly the same thing as if we were doing the question in 3.3 using the factor theorem. So we're going to perform synthetic division using that 0 that we found, which is 2, to find the other factor. So hopefully you remember from last section, this means that if f of 2 is 0, which it is, that means x minus 2 is a factor of f of x. Okay, so when we're doing synthetic division, we just use that 2. And we go back up to the function and write down, that's the dividend. We write down all the coefficients. The coefficients are going to be 1, 2, -5, -6. Synthetic division, bring down the 1, multiply, add, multiply, add, multiply, add. And as usual, we should be getting a 0 for the remainder. Okay, so those values that we just got for the quotient are going to be our quotient coefficients. So now we're going to set this equal to 0 and solve it. So set equal to 0 and solve. So I'm going to start by just setting up everything from the beginning. Meaning I'm going to set the function to 0 and then set it up the way that we just factored it. So the original function here was x cubed plus 2x squared minus 5x minus 6. I'm kind of just coming full circle now and starting from the beginning. So we wanted the zeros of that. We said that x minus 2 was a factor because we found the 0 from the possible rational zeros. And our other factor is right up top. We know it's going to be a factor of a quadratic factor because our original was degree 3, so 1 less. So it's going to be 1x squared plus 4x plus 3. We set this equal to 0. we can actually factor that quadratic as x plus 3 times x plus 1, which is nice because then we don't have to do the quadratic formula. So we're going to set all of these factors equal to 0. We get 2, -3, and -1. So that's going to be our solution set here. So I'm just going to write it as a solution set again. You can just circle the answers there if you wanted to. -3, -1, and 2. So all of these values were actually in the possible rational zeros that we found because they're rational numbers. So they're all up there for us. Okay, so let's do another one. So what I'm going to do is I'm going to do this one out, and then for the next two, I'll pause the video and fill it in and just kind of quickly explain it and then leave it to you guys to check it if you wanted to do a practice one. And then we'll move on to the next thing because these questions are kind of long here. Okay, so here we want to find all of the x-intercepts, all of the roots, all of the zeros of f of x, which is x cubed plus 7x squared plus 11x minus 3. So first step, we want to find all of the rational zeros. So the possible rational zeros are going to be factors of the constant term divided by factors of the leading coefficient. So that's going to be factors of -3, which is just going to be plus or minus 1 and plus or minus 3. And then for the factors of the leading coefficient, that's going to be factors of 1. That's just going to be plus or minus 1. So that's just going to give us possible factors of plus or minus 1 and plus or minus 3. So next we're going to test these. And I'm going to say, I'll start with positive 1. So we have 4 to choose from, -1, 1, and -3, 3. Start with saying I'll do positive 1. Is x equals positive 1 a 0, question mark. So let's plug it in. So we're going to do f of positive 1. So plug that into the function. That's 1 cubed plus 7 times 1 squared plus 11 times 1 minus 3. So this does not equal 0. This equals 16. So the answer is going to be no. Next, I will test is x equals -1 a 0. So plug it in, f equals -1. So I'm not going to actually evaluate it, just for time's sake, you can check it. This does not equal 0, it's going to equal something else. So I'm just going to say no, it does not. Next is x equals 3 a 0. So you can see how it kind of gets annoying if you have to try all of them. F of 3. So if we plug this in, we don't get 0 again. So this is going to be no. So technically, if we got it where all of these were not 0, that's technically okay. A polynomial, if the degree of the polynomial is even, it technically does not even have to have an x-intercept. If it's odd, it has to have at least one x-intercept. So this one will have at least one, but it does not have to be rational. So technically, none of these, it's possible that none of them will work, but obviously one of them will work or else we wouldn't be doing the question. So testing x equals -3, this one is 0. So this one gives us 0. Okay, so next what we're going to do is we're going to pick up just like we did in 3.3. We're given a 0 and we're going to use synthetic division. And we're going to do that to find the other factor. So but based on the factor theorem, we know that -3 is a 0. So we know that f of -3 is 0. This means that x plus 3 is a factor of the function. So performing synthetic division here to find the other factor, it's going to be -3 is the c value. The coefficients of the dividend are going to be the coefficients of the function, which were 1, 7, 11, negative 3. Bring down the 1, multiply, add, multiply, add, multiply, add. And based on the remainder theorem, we know that we should be getting a 0 for our remainder because we already knew f of negative 3 was 0. So the remainder says if we divide by x plus 3, the remainder should be 0. And we're almost done. The last main step here is going to be set equal to 0 and solve. So the way I'm going to do it is the way I did the other one. It's going to be, I'm going to set the whole thing equal to 0 from what we started with, because we were trying to find when x cubed plus 7x squared plus 11x minus 3 equals 0. That's all we got. That's all we started with. We figured out that x plus 3 was a factor, and we just found the other factor using synthetic division. It's going to be a quadratic again because it was originally degree 3. Synthetic division, quotient's going to be 1 less than that, so it's going to be degree 2. So 1x squared plus 4x minus 1, all of that equal to 0. So this does not factor very nicely for the quadratic. So let's set these equal to 0 separately. So we get x equals negative 3, which we already knew. And then we set this one equal to 0. So we're actually going to need the quadratic formula. I'm going to cheat a little bit and I'm not going to write it out. So quadratic formula, I'll write down the formula just in case you forgot it. Hopefully you didn't forget it. Negative b, x equals negative b plus or minus square root b squared minus 4ac all over 2 times a. So plug everything in and simplify. We actually end up getting x equals negative 2 plus or minus radical 5. Okay, so this, I'm not going to write it as a decimal. I'm just going to leave it like this because if we wrote it as a decimal, we'd have to round. Not the end of the world, but still leaving it like this. This is an irrational number, right? So these are two numbers and they're both irrational because of the radical 5. So since they're irrational, they are not in our possible rational zeros. And if they're irrational, they never will be in there. So we wouldn't have been able to find it if we kept on plugging in the possible rational zeros, but we actually plugged all of them in. Okay, so if we end up doing these and we end up having to use the quadratic formula and we get a negative as under the radicand, a negative as the radicand under the radical, that means we're going to omit those values because that'd be imaginary values. So that means they would not have, whatever quadratic it was, would not have any x-intercepts. So writing this out as a set, just so I can kind of circle some stuff, I'm going to write it as negative 3. And we also have negative 2 minus radical 5 and negative 2 plus radical 5. Okay, so for these next ones, I'm going to circle that. For these next ones, I think there's 2 more of these ones. Yep, 2 more. So for these next ones, I'm going to go through and I'm going to pause it right now and I'm going to go through and I'm going to do it. And then I'll just kind of mention the answers and how I got there really quickly. All right, so for this one, the possible rational zeros we found were plus or minus 1, plus or minus 2, plus or minus 4. When we tested them, I found that f of negative 1 is a 0. So I'm going to use that 0 and perform synthetic division. Using that negative 1 as the c value, synthetic division, we end up getting coefficients of 1, 0, and negative 4, remainder of 0. And for that last step, I'm going to use the factor theorem. Since f of negative 1 is 0, we knew that x plus 1 is a factor, which means that we can factor our original that was set equal to 0 as x plus 1 times something. And right above here in synthetic division, the coefficients of 1, 0, and negative 4 correspond to x squared plus 0x minus 4, so just x squared minus 4. We factor that using the difference of squares method, x plus 2 times x minus 2. We set all of those factors equal to 0. We get answers of negative 2, negative 1, and 2. Those are our x-intercepts. Okay, so I'm going to do the same thing with this last one, and then we'll go over that real quickly after. All right, so for this last one, before I move on to the last little topic here, for the possible rational zeros, we got plus or minus 1, plus or minus 1/2, and plus or minus 2. So that's from doing every possible combination with that numerator and denominator for the factors of the constant term over factors of the leading coefficient. And so you may realize that maybe you were doing plus or minus 2 over plus or minus 2. That actually equals plus or minus 1 because 2 over 2 is 1. So that's why there's only 3 possibilities that I wrote out, because the 1 pops up twice. So testing these, it turned out that x equals 1 is a 0 because f of 1 equals 0. So we can perform synthetic division to find the other factor. So for synthetic division using 1 as the c value, we ended up getting the coefficients 2, negative 3, and negative 2. So when we use that to set it equal to 0 and solve, I once again wrote the original problem that we were trying to solve. We were trying to find those x-intercepts. So I factored it as x minus 1 times 2x squared minus 3x minus 2 using those coefficients. And to solve that quadratic, we needed the quadratic formula, and I ended up getting negative 1/2 and 2. So the solutions to that polynomial set equal to 0, the x-intercepts, negative 1/2, 1, and 2. Okay, and the last thing for this section is Descartes' rule of signs. So what this does is it tells us how many possible real zeros there are. So it doesn't tell us what they are, like the possible rational zero theorem that we just did. It tells us how many possible ones that we can have, how many possible positive and negative x-intercepts we have. So what the way that it does this is that it does this by considering the variations in the positive or negative signs between coefficients. So we're going to be doing two things here. We're going to be finding the number of possible positive x-intercepts and the number of possible negative x-intercepts. They're going to be really similar ways that we do it, except just a little bit different. So for the first one, for the number of positive real zeros, what we're going to do is we're just going to take f of x and look at it. We're going to count the number of sign changes between consecutive coefficients. It's either going to be that number or minus that number by an even integer. So for example, if we found that the number of variations for consecutive coefficients was 6, it changed 6 times from positive to negative or vice versa, then that means it would either be 6, 4, 2, or 0. So that's what it means for less than by an even integer. Just subtract 2 over and over again. The way that we find the number of negative real zeros, what we have to do, instead of using the function, we have to evaluate f of negative x. So we have to plug in a negative x and then simplify it. And then same thing, it's going to be the total number of sign changes after that, or less than that by an even integer. Okay, so let's do an example so we can see what I mean here. So for the first one, we're trying to find the number of possible positive and negative x-intercepts for the following function. So we have f of x is x squared minus x minus 20. So we'll do the number of positive ones first. So we're going to consider f of x for positive, and we're going to look to consecutive coefficients and see how many times it changed from positive to negative or vice versa. So starting all the way to the left and working right, we have a positive x squared and then we have a negative x. So we have a sign change here. It goes from positive to negative. Then it goes from negative x to negative 20, so there's no sign change. So since there's one sign change, this means that there's one positive x-intercept, one positive 0. And we'll graph this in a second just so we can verify that. Next one for number of negative zeros. So we have to do a little bit of work. We have to evaluate f of negative x. So plugging in a negative x, that's going to be negative x squared minus negative x minus 20. We have to simplify this. This is going to be x squared. Negative x all squared is just x squared. Plus x minus 20. So looking at the sign changes left to right, it's positive x squared to a negative to a positive x, so no sign change. And then it goes from a positive x to a negative 20. So there's a sign change. So that means there's going to be one negative 0. So we already know that there has to be one positive x-intercept and one negative x-intercept. So if we graph this, this is very graphable. X squared minus x minus 20, just graphing a quadratic. We could factor it and get x-intercepts of 5 and negative 4. So 5, negative 4, and really far y-intercept, so I'm just going to put it down here. So it looks something like this. So it has one positive x-intercept here on the right and one negative here on the left. So x equals positive 5 is our positive 0, x equals negative 4 is our negative 0. So doing this next one and doing the number of positive zeros first. So we're just looking at the function x cubed plus 2x squared plus 5x plus 4. And looking at the sign changes starting with the left. So it goes from positive x cubed to positive 2x squared. And it goes from positive 2x squared to positive 5x. Positive 5x to positive 4. So there are no sign changes. No sign changes. That's going to mean there are no positive zeros. So there's going to be no x-intercepts that are positive x values. Next, for the number of negative zeros, we need to look at f of negative x. So plug in a negative x. And then we need to simplify it a little bit. So we're going to get negative x cubed, so it's a negative to an odd power, so that's negative x cubed without the parentheses, plus 2x squared, because the negative x to an even power becomes positive, minus 5x plus 4. So let's look at the sign changes. So it goes from negative to positive. So there's one sign change. It goes from positive to negative. There's another sign change. And then it goes from negative to positive. So there are 3 sign changes. So 3 sign changes. This means there's going to be 3 or less than that by an even integer. So essentially just keep subtracting 2. 3 minus 2 is 1. So 3 or 1 negative zeros. And obviously we don't subtract another 2 because that would make it negative numbers, which wouldn't make sense. So what this actually looks like is going to be something like, probably going to mess it up. Something like something like that. This would be our function f of x. So as we can see, we have one x-intercept. and it's a -1. So we have no positive x-intercepts, which is what we said. And we said we're either going to have 3 or 1 negative x-intercepts, and we do have 1. So 2 more here. What I'm going to do is exactly what I did on for the last couple of the other one. I'll pause it, I'll fill it out, and then maybe pause it yourself and test if you can do it. And then I'll go over it quickly. And here are the results from that. So for the number of positive zeros, we see that there's 3 sign changes. So that means there's 3 or 1 positive zeros. So keep on subtracting 2. So 3 minus 2 is 1. So 3 or 1 positive x-intercepts. Number of negative zeros, plugging in f of negative x, evaluating it, we see that there's 4 sign changes. So 4 minus 2 minus another 2, that's 4, 2, or 0 negative x-intercepts. So if we were to graph it, it would look something like this. There's 2 negative x-intercepts and 1 positive x-intercept, which agrees with what we said. 3 or 1 positive, it ended up being 1. 4, 2, or 0 negative, it ended up being 2. So all this test does is narrow it down for how many we have. Okay, and then for this last one here, I'll pause it real quick and then go over the results. So for the number of positive zeros, we can see that there are 2 variations, 2 sign changes, which means 2 or 0 positive x-intercepts. For the number of negative zeros, plugging in f of negative x and simplifying, once again there's 2 sign changes, so 2 or 0 negative x-intercepts. And if we look at this graph of it, so not my best graph in the world, but if we look at the graph of it, we can see that there are 2 x-intercepts and they're both positive, and there are no negative x-intercepts. So this agrees with our findings for Descartes' rule of signs. Positive ones, we said 2 or 0, there's 2. Negative ones, we said 2 or 0, and there's 0. Okay, so all done with this section. It was rational zero theorem, and then using the rational zero theorem plus the factor theorem to find all zeros of a polynomial. And then this last thing is Descartes' rule of signs. And that is it for 2.4, or 3.4.